Welcome to the lecture on problem solving and case studies on simulation of manufacturing system. So, in this lecture we will discuss about the problem solving and also some aspects what we need to discuss in case of simulation of manufacturing system. Now, what we have seen that you have different type of distribution functions to represent certain kind of events. Now, the distribution, its mean and variance basically affects the output performance measures. Suppose you have a single machine which is used for serving, for doing the operations by using the tools. So, and suppose the inter-arrival time of the jobs which come on that machine, it has the distribution, that is exponential distribution with mean of 1 minute, and similarly the service time is also exponentially distributed and the we mean with 0.9 minute. Now, in that case the utilization percentage of utilization that for the machine that becomes 0.99. So, basically the inter-arrival time is with mean of 1 and the service time is with 0.99 as mean. So, in that case the utilization proportion of time it is utilized. So, utilization factor is basically lambda by mu. So, in that case lambda will be 1 by 1 and mu will be 1 by 0.99. So, that way you will get it as 0.99. Now, in that case what we see, if we do the simulation for a very long time. So, the purpose of doing this study will be that how the performance measures may change. Now, in that case what is seen is that if you basically solve it. So, while solving you have to take the numbers, this inter-arrival time will come, but that will come in random. So, it may range anything from either from 0 to any value. So, depending upon the distribution function it will take any value and it has certain probability. So, now again that will be taken against the numbers. So, if you basically correlate it with the numbers or stochastic simulation you do, in that case against that numbers it will come. So, you do not know what will come, it is not deterministic. So, in that case if you go, so if you go for the long run, then what you see is the average delay in Q may be quite high value. It will be quite, it has been reported in the examples that it may go quite high. Whereas, if you see the deterministic value, if you look at the deterministic value, then what will happen? There is no Q. So, inter-arrival time is, mean time is 1 minute and service time is 0.99 minutes. So, in fact ideally there is no Q. So, what it says that because these are all probabilistic, we do not know that what time the job will come. So, that can be seen by only simulation. So, in the simulation you can simulate it quite easily, that you go into the Excel sheet, you have the inter-arrival times. So, that will be basically pertaining to certain randomization inputs. So, for that you can have the random numbers and then you can assign them. So, you will have the inter-arrival numbers, inter-arrival times, and this basically is quite stochastic. So, quite probabilistic and it will range from anything. So, that is why it is seen, even it has been reported that it may go as high as more than 50, 60 or even 90 minutes, which is not imaginable if you look at the deterministic approach, like it is coming after 1 minute and every 0.99 minute if it is getting served. So, in that case there is no Q, whereas that Q may go as high as 90 or so. So, basically the prediction of these performance measures depends on the mean and variance of the distribution function what we use. So, that is why this is important when we analyze such systems. So, what we will see that in the case of manufacturing system, basically you have many types of times, like uptime, you have downtime, in the downtime you have waiting time, repair time. Now, all these are basically the times either you are having those data or you do not have those data. So, basically in those times you will have to fit them, you have to assume certain kind of distribution function which is reported that it is normally fits, it normally fits. So, many a times the data is given, many a times you have some data and it is seen that you basically fit many number of times, and then you see suppose some data fits with certain type of distribution and it is tested many times. So, in that case maybe that the mean value for which it fits, that may vary every time little bit. So, we can take the average value in the end. So, this is how, these are the basically approaches which is normally used in case of simulation of manufacturing systems. So, the thing what we need to know that we may face situations when factory data are not available to support either calendar or busy time approach, or there is inadequate time for data collection and analysis. So, these are also the situations which we may come across. So, for that you have basically for modeling the up times and down times, you have the standard probability distribution functions which can be used with specific values of parameters, that we will see that how if we have some data, how we will see that how it fits into it. Before that, let us see one example of another example where a machine is there which is expected to come, and it is said that it will be down for 10% of the time. So, about the machine it is written. So, one machine is there, a machine which is expected to be down for 10% of the time. So, expected to be down for 10% of time. Now, as we see that we may have the data in different forms. So, means for 90% of the time it is up and then 10% time it is down. Now, other data may be given like the interarrival rate of parts, So, that is basically given as suppose exponential, it is exponentially distributed, and that is exponentially distributed with mean of 1.25 minutes. So, exponentially distributed with mean of 1.25 minutes. So, then it means you have a distribution function and it will talk about the times and the associated probabilities. So, you can draw these exponential distribution in computer. So, there are many softwares now available, but even you can do on your own. So, if you go to Excel, you just write exponential and then you can draw it. So, they will ask you for the values against which it has to be drawn. So, x values and then for the lambda value. So, if you put those values, then it will draw against the x values. So, you will have the exponential this. So, that an interarrival rate of parts is suppose given as exponential distribution with mean of 1.25 minutes. Similarly, there may be given as processing time, and suppose processing time is taken as a constant and that is 1 minute. So, processing time is, it may be a variable, it may be following certain distribution function, but suppose it is given as a constant of 1 minute. Now, time to failure. So, time to failure, it is said to be the having exponential distribution, and here the mean time is 540 minutes. So, mean 540 minutes means for 540 minutes the machine will be up So, basically it is using the calendar time approach you have to go. It is not given that in that how much time it was idle or how much time it was busy. So, it is given that simply your time to failure. So, that is using an exponential distribution and that mean is 540 minutes. Similarly, the repair time and repair time may be given. So, repair time is said to be gamma distributed. So, gamma distributed, and as we know in the gamma distribution you have two parameters, shape parameter and scale parameter. So, in the gamma distribution basically the shape changes with the change in the shape parameter values. So, it is said that it is gamma distribution with shape parameter as 2. So, that is alpha and beta we call it, sometimes beta and theta we call it. So, shape parameter as 2 and mean is 60 minute. So, what we see is certainly 90% of time it is up and the 10% of time that is 60 minutes. So, that is ultimately it is down. So, your whole cycle of up and down process is normally you have 600 minutes and then you have. So, that is why your mean length of up down cycle becomes 540 plus 60. So, that will be 600 minutes. Now, you can go for doing the simulation of this problem. So, in that problem basically you will have the time for the ups, that is how much time it was up, and that first of all the time of arrival. So, your time of arrival is basically exponentially distributed with the inter-arrival time as 1.25 as minute as the mean. So, it will vary from anything from 0 to some value where the probability becomes 0. So, we have to have those values and then in that you will have the processing time. So, it will be coming and then it will be coming as the processing time. So, as we know that if the inter-arrival time is lesser values, in that case the larger Q will be generated, and if it is more, in that case the processing will go on and it will reduce the Qs. So, if you look at in that case that if suppose there is no breakdown in that case, so there may be such ideal cases, but then what we will see here we have to how to model such cases. So, what it has been seen that normally if you do the 5, so simulation runs are done. So, if the simulation runs are performed, so what has been basically the values. So, you have some basically output performance measures. Now, what are these typical output performance measures? So, the typical output performance measures for which we are interested will be basically average throughput per week. So, these are the typical output performance measures. Now, what we do here basically 160 hours of simulation, that is 20 days of 8 hour a day. Suppose you are running the simulation and then you are basically finding these output performance measures. So, suppose in a week you have 5 working days, you have 8 hours of running. So, you will simulate for that 8 hours, then it will go for 5 days and then you can go for, suppose if so in 1 week you have 8 into 5, that is 40 hours. Similarly, if you go for 4 weeks, so if you go for 20 days like 4 weeks, so in that case you will have these you need to know about these output performance measures. Now, what are these? So, next will be average time in system. Then you will have maximum time in system, further you have average number in Q and then maximum number in Q. Now, these are the typical output performance measures for which we are interested in, and we need to know that what are these performance measures, what are the values of these performance measures per week. Suppose average throughput, how much of the product is getting serviced and which is going out, like average time in the system, maximum time in the system, and average number of in queue. So, using this values, like if you take the mean downtime as this time to failure as 540 minutes. So, what we seen is that you have different conditions. So, if you take the different conditions like condition 1, and so in condition 1 you can have condition 1 here. So, if you do the simulation that it has been reported in the Law and Kelton exercise, if you do here there you will find it, or you can do on the arena, basically you can work on arena, or you can have your own code and you can solve it. What you see is the value is coming as something close to 1908, that is average throughput per week. Similarly, average time in system is 35.1, and then it is 256.7 and further 27.2 and then 231. So, what this condition 1 is? Condition 1 is using that mean breakdown time. So, mean breakdown time is taken as 540 minutes, and we are taking these values like interarrival rate is exponentially distributed with mean of 1.25 minutes, processing time constant for 1 minute. So, for this 160 hours of simulation, 5 independent simulations were done using different random numbers certainly, and then you average it out and then you find the values. So, you are getting 1908. This is normally the average throughput per week. Now, then average time in the system is 35.1. Similarly, maximum time in the system is 256.7. Average time in the queue is 27.2. Maximum time number in the queue is 231. What is the meaning of this? So, what we see that in the first case your values are 1908, and so this is average throughput per week. If you do the second simulation where, so in that you have the 5 independent simulations. So, if we do another simulation where we do not take any breakdown, so in this case you do not take any breakdown, so no breakdown. So, if that being the case, the system performance measures are given as basically this value are reported as 1914.8, and then this value is 5.6. Now, then this is 39.1, this is 3.6, and this is 35. Now, what we see the difference? The basic difference what we see, now in this case the processing time has been taken as 0.9. So, here in the condition 2 you have not taken no breakdown. So, you assumed that there is no breakdown, and also you assumed that processing time is 0.9 minute. So, if there is no breakdown and processing time becomes 0.9 minute, in that case it is seen that it is going similarly somewhat. And now, what is that meaning? In fact, in that case, since there is no breakdown, so what we see that in 5 days, if you look at, we have the 5 days week, and so what we see is interarrival time, that is 1.25. So, in an hour you get basically 48. So, basically you have 48 arrivals in a day, no, in an hour. So, in the 8 hours you have a number of arrivals. So, you have number of arrivals in 5 days. So, that number of arrivals becomes 48 into 8 into 5. So, that becomes as 1920. So, that is close to that. So, what we see is that is average throughput per week, that basically is your 1914.8, and then processing time is less. So, in normal case what we see that since this being more, it means at larger intervals the product is coming for getting the job done, and then it takes very less time to basically serve it. So, you are getting normally close to that value. So, it is close to 1920 in a week. So, in a week, and that is why you get this throughput as close to 1920 in both the cases. Normally what you see is they are comparable. However, you see that this average time in system, that differs a lot, or maximum time in system, that also differs, average number in queue, and you see maximum number in queue, these are differing. Although maximum throughput you do not see, average throughput you do not see much of the changes, but you see a lot of change in on the other things, because in this case here the processing time is less, and in this cases there is no breakdown. So, basically these values changes, these values change. So, that is how the difference comes. Similarly, it has further been reported that if you have another condition, that is 3, where suppose you have again 5 independent simulation runs, and here the condition is different. In this case the mean breakdown time is basically changing from 540 to 54. So, in that case what happens? So, if it is coming from 540 and it is going to 54. So, condition 3 is your breakdown time, mean time to failure is 54 minutes. And similarly you keep the repair time, so that is service time, and if you keep that time as repair time mean as 6 minutes, now if you do that, what we see here again we have the same condition, we have 54 minutes of uptime and then you have downtime of 6 minutes. So, ratio is 9:1. Okay, 10% of time it is down, but then if you do again the simulation runs for that many hours and you do 5 independent replications and further you do the average, these values are reported as something very close, 1913, then it comes as something like 10.3, then it comes as 76, this comes as 7.3, and this is 67. So, what we see that normally you have although the average throughput is same in this case, but then other things change, because here you have the mean time to failure is less. So, these values changing, these parameters changing, this ultimately the output performance measures are changed. So, what we see that these values basically affect the system. So, now let us see that when we do not have these data, in that case we must have the idea of the distributions as to what kind of distribution basically will fit for certain type of events, like you have, as you have seen here, you have machine up times, you have machine down time, repair time is there. So, there are many situations and many times you do not have the data. So, you must have the idea that which of the distribution will basically fit better. So, exponential as well as gamma distribution with different values of shape and scale parameters has been seen to fit better. Even the gamma distribution is said to be even more flexible. because with the changing shape parameter, the density, the curve takes different shapes. So, gamma distribution basically is seen to be more realistic. So, what has been seen by practice, that if you have the data, if you try to see exponential many a times does not fit very much, especially near that ordinate axis, basically it does not fit much. So, it will meet at that point, but then mostly you will see that maximum values are in that. So, basically the actual values are quite high, having high probabilities. So, that way we will see certain cases where we will see that though how they are changing. Gamma distribution is preferred, as we discussed, because of its flexibility. What we can see further is certain typical histograms which normally has been seen that your processing times, how they are following. So, typically it is seen that the processing time for automotive component follow like this. So, how to see that which distribution it fits into. Similarly, typical histogram of the time to failure you can see here. So, in this case, this is the value of finally what we see, that so we see here that this is the typical histogram for processing time of an automotive component, and this is the histogram of time to failure for a household product. It looks like as if it is exponentially distributed if you look at, but then if you see, if you exponentially distribute, you will see that this curve goes like this. Now, here it goes like this. So, we then but you will approximate it with exponential, whereas the exponential actual line will come here close to this. So, this will go like this. So, most of the time here it is predicting under the value, means it is close to 30 more than 0.35 or 0.36, whereas this graph will come here. Then in that case, in some cases the line will be up and these values of probability will be down. So, in that case it is not said to be a very good fit. So, in those cases you can go for some other kind of distribution, and that is where the gamma distribution is said to be a proper fit. So, in gamma distribution, similarly there is another parameter which is there like repair time. So, similarly some data has been seen of the past, and it was seen that this is normally the time to repair, and normally it is seen that you have some mean value of repair, and then finally it goes like this. How to see that which type of distribution it fits? So, normally it is seen that this gamma distribution with the different shape parameter is very much fitting to such kind of curves. So, what happens in the case of suppose this earlier one, like you have this time to failure, if you see, if you manage it with the basically if you try to draw the exponential curve, in the exponential curve what happens, you have the curves like here, what you see is you have the values high and then it is down, and further you have this down and all that. So, this is how it is going, and so what we see, if you typically draw the exponential curve, it goes like that. So, most of the places you will have the values which is here, and here also it is not able to predict, you have a larger values in this case. But if you try to draw the gamma distribution with alpha as 0.7, so if the alpha is taken as 0.7 in that case, the distribution comes like you have further the gamma distribution will come with, so this is 0.7 and 1 as the scale parameter. So, in that case the curve goes like this, so which basically fits more with such kind of distribution function. Similarly, if you go for this typical histogram of repair times, in case of repair times what is seen is that you have the, if you take the, it does not fit with the exponential distribution. So, what we see is here for certain values, whenever you have the data, you try to fit it. So, many a times it fits with certain kind of gamma distribution with some shape parameter value. So, in that case it was seen that if you draw the gamma distribution with the shape parameter of suppose 1.3, and so it is 1.3 and 1 gamma distribution, mean is the product of 1.3 and 1. In that case it was seen that this curve goes like this. What we see actually, this is showing like such kind of distribution. So, what can be said that normally you will have to do this analysis, and then you have to see that how this fits. So, basically the type of distribution what we use, that basically tells you that how accurate you are going to model it. You will have to check, you must have. So, we have studied about the different kinds of distribution functions, and we should know that what kind of distribution function is better. We can go for variable, but then for variable, as we discussed, it is difficult for mean to be computed. So, we go normally for this gamma distribution in such cases. Now, in the other way, now another thing we need to specify, once we have seen that we know these shape parameters, now we need to specify the beta B and D basically for busy time as well as for the dawn time. So, for that, for these gamma functions, we have certain things what we see. Now, what we see here is that we have one parameter, that is efficiency. So, we need that efficiency E we define as, we can define efficiency as ratio of mu B to mu B plus mu D. So, that is your busy time mean, that is the downtime mean, and similarly you have the busy time mean. So, it is nothing but the long run proportion of potential processing time during which the machine is actually processing the parts. So, this is what the efficiency will be defined as. Now, from here what we see is, we have seen that we have two times, one is the busy time, that is your time to failure, and then you have another is time of repair, and in one case you have alpha as 0.7 and in the next case you have alpha as 1.3. So, this way we have, now E is defined as this, and from here what we get is, you can see that you can get E mu B plus E mu D. So, that we get it as mu B. So, from here we can get this E mu D as mu B into 1 minus E. So, we can get beta B. So, we wanted to have this beta parameter, because alpha B, once we know the mean is alpha B into beta B. So, we can get this beta B as mu B by alpha B. So, once we know mu B and once we know alpha B, so that will be told as E raised to and then mu D divided by 1 minus E into, that is 0.7. So, this is how you calculate this beta B. Similarly, you can have beta downtime also calculation, and that will be basically mu D upon alpha D. So, that is alpha D value is 1.3. So, it will be mu D by 1.3. So, these are basically the values of the other scale parameter along for that distribution. So, this way you can have the main idea about the functions which is to be used, the parameters which is to be calculated, and once you know that, then you can go for calculating the measures of performance as the simulation progresses. Thank you very much.